Hello, wonderful people. Welcome to Cosmology Talks. This is another talk in the CAMELS series, this one by Lucia Perez, a PhD student at Arizona State Uni. As this is part of a series, there's no intro to CAMELS. If you want an intro, it should be on the screen right now, or if not, it's in the description. If you've watched a few of these CAMELS talks, you'll notice that the small box size of the CAMELS simulations is one of the leading frustrations people have. CAMELS is great, but that is a limitation. So Lucia is the person trying to fix this. It's not possible, it may never be possible to brute force this. You can't just throw computing power at it and have an enormous volume simulation that's still resolving individual galaxies. The hierarchy of scales there is just too large, and to do machine learning like one wants to with CAMELS, you need thousands of simulations. So maybe you could do just one, but then doing thousands will take thousands of years where one takes 1 year. So Lucia is using semi-analytic models to try and patch those small scales and large scales together. This sort of work will be imperative for all cosmology in the future as we probe to ever smaller scales, but still need to know about statistics on the larger scales. So this work will only gain in relevance as time goes on, not just for CAMELS, but for all numerical simulation cosmology. So enjoy. Welcome to Cosmology Talks. Lucia, do you want to tell us quickly about your work?
Sure. So, hi, I'm Lucia Perez. And essentially, what I did with CAMELS is I arrived to see what kind of constraints for cosmology we could get with galaxy clustering and all of the neural network machine learning we're doing. And then what ended up happening was I essentially made an entire third hump for CAMELS, a new suite of simulations where we ran larger dark matter only volumes and then used a semi analytic model to fill them with galaxies. And then finally got to the whole trying out to see what kind of galaxy clustering constraints we could get. So this work was done with a lot of people. I want to spend a second sort of emphasizing the massiveness of this work. So the original CAMELS suites, right, are hydrodynamic, fully run simulations that are really, really impressive and get at a lot of that core of the astrophysics we want. But it's still not feasible to kind of do it on a much larger scale just because of like computational requirements and storage requirements. So the path that we took to do this was to run a bunch of and body only simulations. So if you click on the video, this will take us through. Yeah, so it kind of slices through one of these simulations so you can see the kind of beautiful, like large scale structure that the dark matter holds within it. And the semi analytic model from Rachel Somerville is a great way to kind of inhabit it with galaxies in a really robust way. So let's talk about kind of how this sits amongst the rest of the project. So this work sort of sits very much between like the simulations and astrophysics side. So again, we're kind of leaning in really hard into the end body only and going on a much, much larger scale. And then as another way to think about it, the semi-analytic model sort of functions as another model for astrophysics, which instead of, running the full equations for hydrodynamics, you have these like empirical formulas that kind of answer, okay, how does mass move in and out of stars and out of galaxies as a whole, and kind of works as all these formulas that we can tune. So in the same way that CAMELS sort of varied all these little parameters in the two simulations, we vary different parameters in the SAM to get different catalogs for galaxies. The scale of these is enormous. I think the full snapshots that we ran, and also we ran 100 snapshots, not just 35, because we needed that sort of like density and like richness in the merger trees to be able to run the model. I think in total it's something like 500 terabytes. So we have to share the SAM Galaxy catalogs that are only 7 terabytes, and a lot of the like Rockstar merger tree Halo catalog information. So this is a really exciting data product, and I want to tell you about the science that I've done with it. So I kind of put this in context for like why this matters, right? So two big goals for CAMELS that I think are very relevant to this project is first, the goal to try to figure out how to marginalize over all of the unknowns of astrophysics to get at the underlying cosmology. So that's one really big goal of CAMELS. Illustris TNG and SIMBA and even the Santa Cruz SAM are really robust models that independently recreate a lot of summary statistics. But they all kind of, when you compare them apples to apples, they don't agree because we don't really understand a lot of astrophysics yet, and it's a very active field of study. So in a way, we want to try to figure out different summary statistics and methods that kind of cut through all of that to get at the underlying core and meat that we want. And galaxy clustering is a really useful way to do this because, right, in the larger like lambda CDM model and like of how we think dark matter works, right? Dark matter forms, it's most of the matter in the universe. It creates all of this large scale structure, and galaxies form in those wells. And This also ties to another big goal of CAMELS, which is to try to get theoretical predictions for observations, especially on nonlinear scales. So there's a lot of words in there. So the things to think about. So that whole model I just talked about with like how dark matter halos are inhabited by galaxies, when we're looking at really large scale, so like the full scale of the simulation, and even things like Millennium or the full TNG 300 volume, on those super big scales, we can recreate galaxy clustering very easily. We can recreate a lot of these really, really big structures very well. But once we start getting into like actual galaxy clusters or things on a smaller scale, it kind of breaks down. So let's move on to kind of like take these questions and the solution I'm proposing and kind of tie them to the specific project that I'm trying to do, right? So our goal is to think about, okay, we get the clustering of a set of galaxies. Something has to happen between there, but how do we get at that underlying cosmology and astrophysics? So these are a lot of the big questions that my project is trying to answer or help inform, right? So if we have neural networks, which can be a tool to sort of like mathematically connect to these two things, what kind of constraints can cosmology give for clustering, or clustering can give for cosmology? And also, maybe clustering can tell us more about the actual astrophysics going on in galaxies. This has been shown in observations, so hopefully we can see it in these simulations too. And then we can also get into the meat of thinking about how different clustering statistics do. We have all of these summary statistics, and all of them kind of target different things. So we can look at that a little bit too. We can also think about, okay, Lucia has gone to much larger volumes and tried to keep that resolution. How much information do we gain at slightly smaller scales of maybe 1 to 2 megaparsecs? And then also, again, this is a whole new hump for CAMELS. What kind of opportunities start existing for the project and for like the field as a whole?
So when you say that clustering statistics can tell us about astrophysics, is that more or less just turning on its head the normal way one might view it is that, oh my god, baryon feedback is so annoying, it gets in the way of me learning about cosmology, in the sense that the exact same effect it is having on the statistic you're interested in is therefore meaning that measuring that statistic is telling you about baryon feedback, therefore telling you about astrophysics.
So a great example of this in observations is if you compare, for example, like very specific emission line galaxies. So star-forming galaxies that are emitting in like a very, very bright, like O3 line or H alpha or H beta, and you compare the clustering of them and you study it across cosmic history, which you can do with photometric redshift surveys. Their clustering like acts a little differently than you would expect. So they're being influenced by their environment, they're influencing each other sometimes. So that's the kind of thing we're hoping to get into. There's also something just called galaxy assembly bias, which is sort of the idea that, okay, obviously the mass of a halo is the most important thing to decide the clustering of a galaxy, but it's not the only thing that influences it. There are other things, and we're not really sure how those work. So this can hopefully start informing some of that. And again, this is like a very preliminary proof of concept work, and also like the presentation of these simulations. So my data release is sort of happening concurrently, and it's been very exciting and stressful, but it's a really cool project. Right, so clustering is really great because it should help you get at that underlying cosmology, and theory does this very well at very large linear scales. We talked about this. But once you're actually trying to get to smaller scales, then the connection to astrophysics and how the astrophysics actually influences that theoretical connection is very tricky. The great thing is neural networks kind of like just do their own math. They're like, okay, I'll figure out the relationship between these two and give you something else. And obviously, the good thing about clustering is you can kind of check it against theory. And another very important thing that we need to be very aware of with neural networks, predictions that our neural network creates are only as good as our training set. And also, we need to make sure that we can interpret our results and like, can we get interpretable neural networks? That's like a very difficult question. But this is kind of the reason I did CAMEL-SAM, right? This is a very large suite that can actually do the galaxy clustering and minimize cosmic variance. And galaxy clustering can kind of get at both of these things. So I'm very excited about it. Cool. So the first big takeaway, and this is for people who do galaxy clustering, is to not just use 2-point statistics. So a little bit of an introduction for those who aren't familiar with galaxy clustering. We're doing statistics and we're trying to like understand something about what puts these objects where they are without getting caught up in like where every individual object is. So there's lots of different statistics that we can use. The most common are 2-point statistics like the power spectrum, which a lot of projects in CAMELS use. One very exciting one will be entering this project using the electron power spectrum. But the power spectrum is measured with the 2-point statistics and the 2-point correlation function of galaxies. So it's a very common statistical tool and you just do pair counts. And it's a very brief summary statistic. One radius gives you one measurement. But there are other types of clustering statistic. So one very big one that, for example, Paco has worked a lot with Quixote, which is a different set of simulations that tackle something different, is this statistic called count in cells, which is very much what it sounds like. You drop a bunch of cells in your sample and you count how many galaxies are inside of them. And this statistic contains all of the higher order correlation functions. You could argue that it includes all possible information from clustering statistics, but it's very computationally expensive and it's a dense statistic, right? So one distance scale can give you hundreds of points depending on how many numbers of galaxies you're taking into consideration, which is great for full information. But as we've talked about, I'm sure with a lot of people in CAMELS, we need summary statistics, right? You can't give it just all of the positions.
It sounds like this might be a genuine disagreement you guys have within CAMELS, because I'm sure that I've had someone already on today saying the exact opposite of that, that we don't need summary statistics. We're just going to do everything.
It's spicy.
Okay.
Yeah, no,
okay.
I think it's valid. Yeah. The one reason that I think it's worth still pursuing summary statistics is like galaxies are very weird. Galaxy selection is a very tricky thing. And like contamination is always a problem in your galaxy samples. So the good part of doing summary statistics is like there exists that theory behind it to help you deal with all of that. And also there's a very practical thing of like, if I'm doing a very simple one-to-one neural network, if my first array is 10,000 things long, it just gets very unwieldy to train.
Yeah, presumably there's also the human level of understanding, right? Like if I have a neural network that just takes the pixels on the sky and tells me the value of omega matter, and it's 6 sigma bigger than the Planck value, okay, something's broken. But if I have 3 different summary statistics and the 2-point correlation function is bang on, counts in cells is 2 sigma away, and void probability function is 8 sigma away, then I'm like, okay, it's the empty regions that are the suspicious ones. So summary statistics point you in the direction you want to look at, I guess.
Exactly. And another good thing about at least like clustering summary statistics is like people have been measuring it for like decades on tons of different galaxy samples and have done all the hard work of choosing very carefully. So taking advantage of all of that hard work is dope. Yeah, so I think the last clustering statistic, which is like my baby, is the void probability function. It's a very simple statistic. You drop spheres and you only count the empty ones. How likely is a certain cell to be empty? So in that way, it's sort of like the 0th moment of count in cells. It's very simple to calculate. And it's a, one radius, one measurement, like the 2-point correlation function. So I'm single-handedly trying to bring a renaissance to the statistic, I feel, but I'm going to show you it ends up doing really well.
I worked on things called voids in the past, and I think your definition of void is the most pure definition. It's like it's where the word came from. It's like it's a region of the universe that is void of stuff. Whereas nowadays voids just means large scale underdensity or even small scale underdensity, but just underdense regions. And those are different things, I guess. So
they're very different. Yeah. So there are people in CAMELS who work on what are called cosmic voids. So for example, in this figure, those would be the underdense or very empty appearing regions. But in this function, it is just a mathematical concept. Like it is, you drop a fake circle and you see if it's empty. That's it. It's like a very clumsy statistic. Thank you for that clarification. That could confuse people. Yes, so this is what these statistics look like, right? So for example, you measure all of these in all the simulations. In this case, the count in cells is at 1 distance scale, but you can see the amount of information, the differences we're already seeing across all of the different cosmologies and those input SAM parameters that deal with star formation rate or like radio jet feedback. So essentially what I've been doing in this work is taking all of these clustering statistics and just like feeding them to a neural network. It's like, okay, I have my galaxy sample. I measured its clustering. It's a summary statistic. Can you tell me what it predicted? And some very interesting things that we found. So the 2-point correlation function does exceptionally well, like compared to the other two at getting sigma 8, one of the cosmological parameters of CAMELS. But it turns out the VPF and count in cells really pull their weight at pulling omega matter through. So I can talk a little bit more about how these constraints compare with some of the other works. But we're like omega matter is basically very similar to a lot of the other projects, 5%-ish. And sigma 8, we either like some people do much better and some people do much worse than us. So it's like a very interesting sort of like assessing how all of these work.
Do you have a physics intuition as to why it goes that way? I mean, maybe sigma 8 and 2-point correlation function is obvious because it's measuring a power spectrum, and sigma 8 is a measurement of a power spectrum. But why the void and counts and cells do better at omega matter?
I think it's because like the VPF and Cowan cells are very sensitive both to like the influence of number density, but also like omega matter, right, is like the amount of matter in the universe. So like that is a very important feature of a lot of these things. So I think I don't know, this is part of the paper that I'm still like working on articulating.
It does make sense. If you've got more matter, there'll be more galaxies in a cell. If you've got more matter, there'll be fewer voids.
Yeah, I think the thing that was very surprising for me is that a lot of the time the VPF did better than counted cells, which you would not expect because counted cells like contain so much information. But the problem with counted cells is like it's so dense that I had to choose how many distance skills to do it, but the VPF kind of catches it all. So I don't know. It's a very interesting experiment. Again, there's tons of statistics we could add, but in this first initial try, these are the ones I'm familiar with and I like, so we went with it. So the next big takeaway, apart from using more than 2-point statistics, is also just like showing what our constraints are like. So here's one example. These are stellar mass selected objects from the semi-analytic model. And again, in this case, I think it predicted all 5 parameters at once, but it did really well on the cosmology. So in this case, these are about, I think, 5 to 8%, like respectively. So this is really encouraging as like a first round. And also one thing to note is like stellar mass clustering does quite well. Obviously, if you do dark matter only clustering, you're going to get the best possible constraints like that you can. So it's really encouraging for us to see this. And like there's a lot of little explorations you can do. Like what if you do star formation rate selected galaxies? But this is just to sort of show you like, hey, this experiment worked. Like galaxy clustering gets at the cosmology. It marginalizes over astrophysics. But the next big takeaway is like at least the SAM parameters do influence the clustering. And the neural network is able to pick out sometimes the slight influences. So for this specific neural network, it was trained on the first 750 of the CAMEL SAM simulations. It's validated on 150, right? And that's just what chooses the best neural network. And then the test set, the like final 150 that are kept completely separate and never looked at, this is how well that neural network does at predicting the parameters, right? It takes in the clustering, it does whatever internal math it does with all the gradients, and it gives you a prediction for the input parameters. So in this case, I'm using one of Paco's very well crafted likelihood-free inference loss functions, which essentially give us like a nice little error bar to like approximate the standard deviation of the posterior mean. So big things to take away here. Omega matter, beautiful. Sigma 8, quite good. And the supernova parameter, we weren't sure how much they would influence it because a quirk of how the semi-analytic model runs is that it runs on the halo merger tree. So in a way, you can kind of think of the SAM as sort of like painting galaxies on by very carefully taking all of these things in. And for example, like the supernova parameters here affect the amount of mass offloading from a galaxy that's tied to its circular velocity from the halo. So all of these things kind of work together. And even though that AGN parameter perhaps isn't doing so well with this selection, there are other selections that pull it out a lot more. So it's been a very interesting thing to sort of like learn for what selections different parameters really influence it, and just to like see it period is a great surprise and joy.
These are things that in the real world we could actually go observe and then therefore in principle measure ASN1.
Yeah, we can talk more about that at the very end for like the things that keep me up at night and I think about a lot. But yes, that's exactly the reason that I wanted to do galaxy clustering is like these statistics just like exist. They're out in the literature. Yeah, the quirk about it is the galaxy selection. But let's like do one little last thing to kind of wrap everything up, right? So I told you about the 2 big CAMELS goals I wanted to focus on. One is how do you marginalize over astrophysics to get at the underlying cosmology? And also thinking about creating these theoretical predictions for observations, especially on non-linear scales where like these astrophysical things are having more influence. Galaxy clustering is my answer to that. It's a very useful one. It's very well observed. So I've shown that with the CAMEL SAM, the new hump to CAMELS, neural networks and galaxy clustering can marginalize over astrophysics and also like get a sense of what it's doing. And this is really exciting work. I'm excited to like maybe work with theorists to start tying this more into like creating predictions for these non-linear scales. But this is a very exciting proof of concept work. And like the big takeaways, this galaxy clustering gives really similar omega matter constraints as like the CAMELS hydrodynamic 2-dimensional maps that Paco worked on, and the electron power spectrum. And sometimes we get even better sigma 8 constraints. So it's very, very cool. So I guess now the thing I can tell you about is like, I guess the relevance to like longer term things. So, you know, if you talk to Paco and he's like, all chill, what are your dreams for CAMELS? Like, I think if he had it his way, he would have gigaparsec size volumes with full hydrodynamics. That's not really possible yet. So was a really important step to start moving towards larger volume simulations. But the other thing is like hydrodynamic simulations are really, really robust and like they're kind of the gold standard in a lot of ways. But if we're a little more flexible in what we think about models for galaxies in astrophysics, then doing something like semi-analytic model is a great way of tying that. And also something that I think a lot about, like a lot about, is like what needs to happen for me to have a neural network that can actually take in observed galaxy clustering, right? If I have O3 emitters at redshift 0.92, and I've measured the void probability function and their angular correlation function, what needs to happen for the neural network to be able to actually properly measure the cosmology of that? The training data needs to be like valid.
Yeah. And you mean that, say, Illustris and Simba and therefore CAMELS isn't necessarily correct enough description of our actual universe to...
Oh no, they totally can be. Absolutely. Okay, so one thing I will say is like I think the goal to get emission line galaxies into CAMELS, we've started that. We had a collaborator, Sheila Hirschman, who created that, and I think that's a project to revisit. The thing about the original CAMELS suite is it's only 25 megaparsecs per side, and cosmic variance becomes a big issue. So like I tried doing the galaxy clustering predictions, but it's too noisy. It's very hard to do galaxy selections and have enough simulations make it through. So one good example of this is like if you wanted to just do like stellar mass, just any stellar mass in your galaxies, Simba will very easily have thousands of galaxies in every simulation volume. But Illustris TNG will have a bunch that only have like 50 galaxies that have any stellar mass. So that's the challenge with galaxy clustering specifically, which is why these simulations were sort of an answer to that. So at least right now, if I'm thinking, how do we get good enough training sets for galaxy clustering, the answer is a volume this large. But also like getting good mock galaxies, right? Because for example, just doing a basic stellar mass cut may not be a good way to get an emission line galaxy. That takes a lot of consideration, and I spend a lot of time thinking about that.
Cool. And was that then the answer to the question that I was going to ask at the end of like what keeps you up at night on this topic, and what would you like to talk about with other experts in or outside CAMELS?
I think with experts, I just want to know, like, how have you found a good shortcut for getting like accurate galaxy samples out of simulations? Because it's a really tricky thing to do. So yeah, that's what I want to hear from experts is like, how do I get your galaxies to be faithfully recreated as a whole in these kind of simulations if you only know about the dark matter?
Cool. Well, thank you for the great work and great talk, Lucia.
Thank you. This is delightful. Thank you for your patience and for listening.
Thanks for watching. I hope you enjoyed that. There will be a live discussion of all the CAMELS talks sometime probably in February or March, featuring all of the speakers of all of the talks, as well as other invited adjacent experts. If you want to be informed about when precisely that'll happen or other mini workshops associated to other cosmology talks, let me know and I can put you on a mailing list. If you want more CAMELS talks from this series, there's a playlist linked in the description and a video probably being suggested on the screen now. In the meantime, if you like this, don't forget to subscribe and click like to let YouTube know to feed you more content like this from this channel and from other channels. And have a great day.